Okay, so in this video, we're going to take a look at isolated DC-DC converters. Well, we're going to begin the discussion of isolated DC-DC converters, and we're going to look at the flyback converter. And this is the first, this is the most logical place to begin the discussion of flyback converters when stepping from the non-isolated DC-DC converters into the isolated DC-DC converters sort of topic. So, first of all, what is an isolated DC-DC converter? So here's an example of a circuit, and this is the flyback converter circuit. But the thing that makes this isolated is the fact that there's this transformer here, which has been drawn in a green sort of box, and it's a certain model of a transformer with the leakage inductance there. But basically, the transformers add a couple of benefits. One is that there's electrical isolation, so there's no direct connection between the input and or the two terminals, I should say. I shouldn't say input and output. So there's no direct electrical connection between V1 and V2, and so that's required in certain applications such as battery charging. I shouldn't say second because there's multiple benefits, but another benefit of having transformers is that you can create multiple related outputs in a fairly simple manner. So you can have multiple winding or transformers that have multiple windings, and you can essentially have multiple outputs that are all related to one another because they're being driven by a single, let's say if you have like a 1 to 3 transformer. So on one side you have a single winding, on the other side you have 3 windings. So those 3 windings will all have some related voltage or current related to one another, that is, based on whatever is driving it from the primary, let's say, in that case. So when you look at this type of configurations, the transformer windings cannot have DC voltages because the magnetizing inductance is a short circuit at DC. So when I'm saying magnetizing inductance, I'm referring to this thing. So let's call it L mu. So L mu is the magnetizing inductance, and so if you can see very clearly if you applied a DC voltage here, you see very clearly that inductors are short for DC. We know that, and you see that you would not be able to have any sort of DC energy or DC voltage develop across the terminals. And so we therefore need to create an AC voltage with no average from DC sources. So if V1 is a DC source in this case, you need to somehow establish an AC voltage. Let's call this, let's call it lowercase v1. Or we can even call it VP, let's say, because that's for primary, let's say. And so you need to develop an AC voltage for VP, and that AC voltage cannot have a DC component, right? So the switches that make this AC type of voltage will also control the conversion ratio. So we're we have these restrictions, so to speak, as to how we're going to approach these type of problems. And so there's 2 main types of transformers that are used. One is I guess, if generally speaking, one stores energy and one won't. So some are just for isolation and some are used to store energy. In a case like this, we'll discuss in a second that this one does need to store energy. So in a case like this is a flyback converter, and so the flyback converter usually has what's called a flyback transformer. So what is the flyback converter? This is exactly the flyback converter that you're seeing in front of you here, and essentially what it is it's an isolated version of the buck boost converter. So you can see it pretty easily if you just imagine that remove this transformer for a second and leave this inductor here, and then connect this diode straight there and connect this terminal straight there. And that's exactly what a buck boost looks like, except for this diode being flipped. But we take care of that flipped diode and the flipped output voltage by just flipping the terminals here. So essentially what we've done is we've taken a buck boost, and instead of using just a standard inductor, we're using the inductance of this transformer in place of that, and then we're going to have a transformer in there as well. So there's no electrical connection between the primary or V1 side and V2 side. Okay, and so you essentially you use the magnetizing inductance to act as the filter inductance that you would have had in the buck boost converter. And so if we look at this, and if we label this Q, so when Q turns on, you imagine you have a short circuit here. And what happens is this current that comes in from V1, let's call it I1, will flow through here. and we can call that I mu, right? And so as that's happening, so if you applied a positive voltage there, you would then apply a positive voltage this way here. Maybe we can change the color here. So the positive voltage would develop in that orientation on the secondary side, and that would force the diode to turn off, or it would just force it to be off. So what that means is when Q is on, the diode, we can call it D, I guess. The diode D is going to be off. Okay, and energy flows into L mu. So that means the windings of the transformer start to store energy. And this is why I was saying earlier that these type of transformers need to be able to store energy. So the winding of the transformer stores energy while Q is on. Now when Q turns off, we'll see that this would obviously become an open circuit. So if this is an open circuit, no current flows through there anymore. And we also know that the inductor current, or the current in any inductor, has to be continuous. And so what that's going to do is, as soon as that switch turns off, or Q turns off, the inductor current I mu is not going to have anywhere to go anymore. So the magnetizing, we can call it the magnetizing current, it doesn't have any path on the primary side. So what happens is the magnetizing inductance releases all of its energy in the secondary winding, and that forces D to turn on. So what happens in that case is this, the voltage here basically switches polarity because of the direction of the current flow, and you end up having current that would drive through, D to turn on, essentially. Now, that would then obviously send the current to the load, and then you would have sort of an exchange between V1 and V2, an exchange of energy. Now, the reason this is called a flyback converter is, I mean, it's a historical reason. So old school CRT tubes and such used to use high voltage transformers, and they had a sort of beam that would, well, that's how CRTs work. There's a beam that kind of directs the image that you're looking at, and so what would happen is the spot on the screen that would usually that would usually like sort of develop as a result of the picture being projected there would fly back, so to speak, to form a new line every time a new line was required. And so for that reason, I mean, it's a historical reason, they call it the flyback converter. You can also call it the isolated buck boost. I mean, essentially, that's exactly what it is. So conveniently enough, since this side and this side are isolated from one another, you don't need to worry about sharing a common node here, right? And so what that means is we can move things around as we want to make them a little more convenient for ourselves. And one of the challenges here with this type of topology is that the potential of this, of the drain source of this transistor here, is not referenced to ground. And usually what that means is your gate driving circuit will have to be a bit more complicated. So to make the gate drive circuit a bit simpler, what we're going to do is we're going to reorganize this side so that this is going to be referenced to the negative rail, so that when you apply a signal to the gate here, the gate source voltage is a bit more straightforward to, and a bit more simpler to ensure that you can actually turn this transistor on. So the way we do that is we redraw the circuit in the following way. So this capacitor stays here. This transformer stays there. And what we say is, maybe we can draw this a bit bigger then. What we do is, instead of that, we take the transistor and we connect it here. And so the transistor is now connected here, and that's connected relative to the negative rail there. And so what that does is, when you're applying a voltage to the gate, and you have to ensure that VGS is greater than a certain value, whatever that value may be for that transistor, it's much more straightforward to ensure that this voltage is whatever it should be than it is to ensure that this voltage up here is whatever it should be. So this is a much more straightforward, simpler, and more stable way of gate driving. And so on the secondary side, we keep the exact same configuration, so nothing changes there. So all we've done is we've moved this transistor, and the reason for that is to simplify the gate drive circuitry. Now, this obviously V2, and the key on this thing is that you have this reversed connection there. And so this we call, let's call this I mu, let's call this L mu, and of course we know that this whole thing is our transformer. And of course we know that transformers need to have turns ratios. So the turns ratio of this, I mean, you can define them n2 over n1, but what we're going to do is we'll call this n to 1 for the purpose of this analysis here. So there's n turns on the left side and there's 1 turn on the right side. And that's just a normalized sort of way of doing it. I mean, of course, it doesn't necessarily have to be 1 turn there. It's just a ratio at the end of the day. So it could be like, it could be like 100 to whatever you want it to be, as long as the ratio is 1 to n is satisfied. And n is usually like n2 over n1. So n itself is a ratio, but then we just normalize it so that it's simpler to sort of write and to consider, I guess. So here we're going to apply a gate pulse, and we're going to do this just to sort of more clearly establish what it is that's going on. So this is our circuit. Now what we're going to do is we're going to draw our waveforms as we usually do. We're going to analyze it the same way we usually do. Nothing changes as far as that's concerned. So even though there's, like, I mean, the circuit looks a bit more different, a bit more complicated than what we're used to, we can still approach it the exact same way. We still analyze it the exact same way. And you'll be kind of pleasantly surprised to know that most of the relationships that we have for the non-isolated buck boost can actually be used for the buck boost as well. But we're going to prove that first. Okay, so let's look at some waveforms. And if we look at, what do we want to look at? There's a couple of things. So the first thing we want to look at is the gate pulse, sort of gating, or the switching gate drive, whatever you want to call it, waveform. So the first thing we'll look at then is, let's call it G. Okay, and as we have done in the past, we're going to look at, we're going to basically split it up into two parts. We're going to split it up into dt and then T. And so D is the duty cycle of the transistor. And we can kind of do it like this. So if we look at G there, we can look at IP here, let's say. And maybe I don't think I included some of the things that I want to look at. So that's that. IP is this current here. And what else do we want to look at? We have I mu, and then we have IS, which is the secondary current. We can call it IS there, right? And so with these three currents, you can kind of develop whatever type of relationships you want. You can understand what the different volt-second balance equations and all that kind of stuff look like. But the currents tell a pretty clear story. We'll look at VP as well. I don't think I labeled VP, but VP is going to be the voltage across L mu. Maybe we can get rid of this for a second and call this, let's say, VP, or it'll be across the terminals really, which is also across L mu, right? So then we can say that this is I mu there. Okay, so the gating pulse is applied, so the transistor should be on during this time, and then it should be low during this time. That's how we define the duty ratio for the most part. In some cases we do something different. For the most part, we look at it like this, okay? And so the gating pulse is between 0 and 1. I mean, we look at it as sort of as a logical equivalent, but in reality it'll be some real voltage, like 10 volts, 20 volts, whatever your transistor requires. So this is IP, and we also want to have, maybe we can copy and paste this here. So we also want to have a couple of other things. So we want to have VP, and then we want to have we want to have I mu, and then we want to have IS after that, but we'll look at that after. So VP is this one here, and I mu is this one here, and we're going to have some sort of breakpoints that we want to include as well. But the thing to take away here is that when the transistor is on, when this transistor is on, IP will flow in like this, basically. So it'll come from this positive terminal, it'll go down through L mu, and then it'll go through this transistor, and then it'll have a closed path there. And when the transistor is off, IP doesn't really have anywhere to go because it can't really form a closed circuit. So what happens is I mu instead starts flowing through this side, meaning IP is only non-zero for as long as the switch is conducting. Okay, so when the switch is conducting, you'll have essentially, because this is a constant voltage applied to an inductor, you have a ramp increase of the current, and the points through the sort of upper and lower maximum, minimum, however you want to call them, of this we call I mu P, and we can call this I mu L, or we can call it N, whatever you want to call it. Let's call it L. So peak, and then L is for, I guess, lower. And so then it goes down to 0 because it's not conducting anymore, and then it goes 0 there for that much time, and then it'll jump back up here, and then it'll continue on as it has before. Okay, now what happens during this time here? So when this transistor is closed, you end up having that Vp ends up equaling V1, right? Because what you have is that there's a path that's actually connecting there, but otherwise you can't develop any voltage there, right? So if this is on, then Vp equals V1. If this is open, then this is open. You don't know what the voltage drop here is, and you can't really make a conclusive statement about what Vp is equal to. Well, you can, but I mean, we'll look at that after. So what happens is when the transistor is on, Vp ends up being V1. Okay, so let's draw V1 like this. And then what happens when the transistor turns off? So if we go back up here and we look at our circuit here, we said that when this transistor is on, this negative rail of V1 connects to Vp here, and so you have V1 equals Vp. But as soon as this opens up, what happens is this diode is forced to turn on. If this diode is forced to turn on, we see that Vp ends up being negative of this voltage that's applied here. And so if we call this voltage here, let's say Vs, then it ends up being negative Vs because of the flipped dotted convention. It's a little hard to see because we wrote over it there, but the dots of these terminals are flipped in this case, meaning the voltage polarity on either side of the transformer is flipped relative to one another. So what that means is you also have this turns ratio of N. So what happens during that time that the transistor is off is that the diode turns on, and the diode turning on ends up creating a voltage across the transformer, and that ends up being a negative voltage. And so that negative voltage, so here we said this was going to be V1, and in this case it ends up being negative NV2, right? Because the voltage on the secondary, sort of, I guess, technically secondary here, I guess, because we're going to call this the primary and this is the secondary. This V2 ends up being connected directly to the transformer via this diode, meaning Vp ends up being negative the voltage on the other side of the transformer. Okay, so that is Vp. And then we have I guess technically this NV2 should be a little bit larger. I mean, it all depends on the turns ratio. And I guess in a case like this, it is more accurate, so maybe we should do it like that. So let's move this down, and maybe we can draw it a bit more to scale, so it makes a bit more sense, because N times V2, I would imagine, should be substantial, relatively speaking. Should be something, I guess, in the same order. It shouldn't be so much smaller or bigger. I guess it all depends on what the turns ratio is, but in a case like this, you can kind of imagine that NV2 is larger than V1. So why don't we call this minus NV2? Okay, and maybe this has gone too far down now. So why don't we shift this up? Okay. Now, this continues, obviously, because this is the thing we're interested in. So now what happens to I mu during this time? Okay, so I mu here, remember, when the positive voltage is applied here, this current I mu will increase. It'll ramp up linearly like IP does. But as soon as this transistor is turned off, there's an open circuit here. The diode, the transistor can't carry any more current, and the diode is forced to turn on. And then what happens is this I mu will discharge through, or the energy that's stored in this winding will sort of dissipate on the secondary side, and that'll cause IS to decrease, because also remember VP goes negative during that time. So a negative voltage applied to an inductor results in a negative slope ramp. And so we expect then that I mu will, during this time, it'll increase like this. And then during the second part, so during dt, it'll, 1 minus dt, it'll ramp down like that. And then it'll obviously increase up like this again. But I mean, it's just a repeating pattern at that point. And of course, this has to be I mu p, and this has to be I mu L, let's call it. Okay, and that's for I mu. And the last thing we're going to look at here in this case is this IS. Okay, so IS, and again, IS is sort of the other half. So you can kind of imagine already, I mean, this is very familiar. When we looked at the buck boost, we saw that the switch currents and the diode currents were sort of half of the cycle each, or sort of one portion of the cycle. So in one side you have the inductor current looks exactly like the switch current, and the other side the inductor current looks exactly like the diode current. It's the exact same thing that's happening here. So what happens in this case is 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 0 when the transistor is conducting, and then as soon as the diode starts to conduct, IS becomes non-zero, right? And then it'll sort of ramp down in the exact same way as the inductor current does, like this, and it'll be 0 again at that point. And again, in this case, you have, well, not again, but in this case it's slightly different. Here you have N times I mu P, and you have N times I mu L, because this is the sort of reflected version, right? So it's on the other side. And so, of course, this is dt, and this is t. So this is what the overall waveforms, or I guess the main things that you want, main waveforms that are of interest, look like for the flyback converter. So again, like I mentioned, this converter's transformer is required to store energy, and they're usually called flyback transformers. They're a special kind of transformer. They usually just have a lot of windings. They're wound on a certain type of core. You can find them in different types of CRT monitors, for instance. So if you have an old TV or like an old computer monitor, you can open it up, and there are flyback transformers in there. I would highly recommend that you be careful with them, because they can produce very high voltages. They're often used in like these Tesla coil type hobby projects and such as well. They're very useful for that. But again, please be careful with that kind of stuff, because they can produce very high voltages, and those can be dangerous, and usually are dangerous. Another thing is that the core of this material, or of this transformer, is usually gapped, because it's required to store energy. And so what I mean by a gapped core is, so a transformer core usually looks something like this. Well, if it's a non-gapped version, it might look something like this, right? And you might have like the winding something like this, and then you have like another winding like something like, well, let's go out like that, and you might have a winding that looks something like this, right? So this is a non-gapped version, because there's no gap between here. So, but what's done usually in the case of a flyback or any sort of transformer that is required to store energy is they purposely put a gap in the transformer core. What that does is that creates a sort of higher, you can store more energy basically in that type of, in a core like that. So we can get rid of that and draw it from scratch, I guess. So a gapped transformer core might look something like this. Usually, I mean, the gap can be in different places. Let's imagine it's in the middle. Okay, so the outsides are like that, and there's a gap, like a literal gap in the middle. Okay, and so then the flux, basically, you can store more flux and things like that is the purpose of this. And you would again have your windings that look something like this. Something like that, I guess. Right? So this gap here, you would have the flux here, and so you can store more magnetic energy and things like that. So that's sort of important in an application like this, and it's a sort of practical thing. But why don't we look at this for a second and establish the conversion ratio. So we're going to apply the volt-second balance to this VP, because VP is the voltage across L mu. essentially, right? And so what we have here is we have V1 times dt plus minus nV2 times 1 minus dt equals 0. And if you solve this and rearrange this, you'll get that V2 over V1 equals 1 over n d over 1 minus d. And this is exactly the conversion ratio that is for the buck boost, except for this new 1 over n term. And again, this is for CCM, so this is clearly a continuous conduction mode. You can see this inductor current never reaches 0. You can do the exact same analysis for a discontinuous conduction mode of the flyback converter, and you would get something that would be similar to the non-isolated buck boost converter, but with discontinuous conduction mode. So I mentioned earlier that there's a sort of convenient thing that lets us use the exact same sort of results of the buck boost converter, so long as we sort of account for the transformer. And so the way we do that is any output voltage, so let's say any VO, let's call it VO, or why don't we just do this? So if you're going to use the buck boost equations to analyze the flyback converter, you replace every VO with NVO and replace every IO with IO over N. So that's the output currents and the output voltage. That's what I'm kind of referring to. So effectively what you're doing is you're eliminating the effect of the transformer while accounting for whatever it does to your circuit, right? So it does it boosts voltage, and then it boosts voltage by the number of turns, and it kind of steps down current by the number of turns n. So for example, if you recall, we had an equation, IOB max was TVO over 2L for the buck boost. Now, if I just say this is VO prime, and I call this IOB max prime, then what I can do is I can call this TNVO over 2L, right? Or if you remember, the conversion ratio in the discontinuous conduction mode was VO over VDC. That's what it always is, of course. VO prime, though, times IO prime over IOB prime max, right? And so what you end up getting then is you have VO prime, which is NVO over VDC, and you have IO over N, and then you obviously have the equation that we just wrote above. I won't write it again here because that'll make it messy. IOB prime max there. So what that does is, that allows you to use the exact same results that we've already developed, or if you know the buck boost, it allows you to use the exact same results to conveniently analyze the flyback, and then you see that the transformer doesn't really add very much complexity to the whole situation. You just have to kind of understand or remember to make this sort of adjustment whenever you're doing the analysis. So overall what we did was we established that this can be, or this is a sort of topology that is an isolated version of the buck boost converter. We slightly moved things around to figure out a more convenient way, at least as far as the gate drive is concerned, a more convenient way to implement the circuit. We stepped through some of these waveforms to figure out what the behavior of the overall circuit was like, and again, it's very reminiscent of the buck boost converter itself, the non-isolated version. Based on VP, we did the volt-second balance, and we found that the conversion ratio in CCM is exactly as it was in the non-isolated version, and just with this 1 over n factor, which again is consistent with the NVO. So that would be NV2, it's the output. But in our other equations, you'll notice we've used VO and VDC in the practical circuits. So this would be NVO over V1, and so you'd end up with 1 over n there. And then any IO over n, any IO becomes IO over n. And so we can prime those sort of just to say that whatever prime equals the version of the variable that accounts for the turns ratio. So VO prime equals NVO, and IO prime equals IO over N. And so we established these two relationships. Right, so this is a very useful converter overall. You can produce very high voltages with it. I mean, it's a very simple converter. it's a good starting place for the isolated converters topologies in general. And so once you can understand how this thing works, you can start looking at more and more complicated topologies afterwards. So I hope this was helpful. If you have any questions, leave them in the comments below. Like and subscribe to support the channel, and we'll see you in the next one.